All right. All right, so Charles's law, volume and temperature. Dimitri, what two variables are being held constant here?
Pressure and amount.
Pressure and amount. And for amount, we can think of that as moles, right? So pressure and moles of gas are being held constant. Now, let me turn on my camera here. For those of you without the handout in front of you, there's a section in the middle of the handout that talks about the fact that we need to use a special unit for temperature. Okay, so let's stop and think about for a minute about what exactly temperature is. Okay, if I ask you what is temperature, most people who don't know a lot about it would just say it tells you how hot or how cold something is, temperature, right? That's not really what temperature is. Temperature is a measure of the average kinetic energy of particles. That's what temperature is. In fact, there's an equation. You can jot it down on your handout if you have it there. The average kinetic energy, and I'll talk about that in just a moment, is equal to 3/2 times R times T, capital R times capital T. That's an important equation. We'll come back to it later on again, but the R in that equation is called the ideal gas constant, the R. So it's just a constant, and we're going to see it again in a few minutes. So that's the ideal gas constant. So the takeaway message from this simple equation is that temperature determines average kinetic energy. That's what this equation is telling us. So what is temperature? It's a measure of average kinetic energy. Well, what is kinetic energy? Does anybody know what kinetic energy is?
The real energy that is produced.
Say again?
The real energy.
The real energy? No, not quite. So there's different types of energy. The two big ones that people talk about in physics a lot are potential energy and kinetic energy. One simple way to think about it is if you have a ball sitting at the top of a hill, right? A ball is just sitting there at the top of a hill. That ball has zero kinetic energy. It has zero kinetic energy because it's not moving, okay? But it's at the top of a hill, so it has a lot of potential energy. Okay, the ball at the top of the hill has very high potential energy, depending on how high the hill is, and zero kinetic energy because it's not moving. If you give the ball a little nudge, it will roll down the hill to the bottom of the hill. As it goes from the top of the hill to the bottom of the hill, its potential energy is going to go down. There's less potential energy at the bottom of the hill than there is at the top of the hill. So the potential energy is going down. What's happening to the potential energy? It's being converted into kinetic energy because the ball starts moving, and it starts moving faster and faster as it rolls down the hill. Kinetic energy is the energy of anything that's moving. Okay? Any moving object has kinetic energy. The faster it's moving, the more kinetic energy it has. Okay? There's, in fact, in a physics class, there's a different equation for kinetic energy. It's 1/2 times mass times velocity squared. This is a little v for velocity. Okay? This formula for kinetic energy is the kinetic energy of an object. So an object that has mass and velocity, you can calculate its kinetic energy. Okay? If you think of a gas, all the particles in the gas are randomly flying around the container, aren't they? We said gas particles are constantly in random motion. So the particles all possess kinetic energy. Do they all possess the same kinetic energy? Does every particle in the container have exactly the same kinetic energy? No. It's like people running around in the gym. Some are moving faster, some are moving slower. They're not all moving with the same speed, so they don't all have the same kinetic energy. And the same is true about particles in a container. They're not all moving with the same amount of energy. So there's an average energy of all the particles that are there. Does that make sense to you? And that's what this formula is telling us. The average kinetic energy of all the particles in the container depends on the temperature. If you raise the temperature, the particles have more energy. If they have more energy, they must be moving faster. Does that make sense? So temperature is about kinetic energy. The more kinetic energy, the higher the temperature. And the higher the kinetic energy, the faster the particles are moving. The ball sitting at the top of the hill had zero kinetic energy. Why? Because its velocity was zero, right? If you have zero velocity, you're not moving. Your kinetic energy is zero, isn't it? Now, suppose you take those particles that are flying around the container, they have an average kinetic energy at some temperature. Suppose you cool down the system. Then the particles will slow down, won't they? Cool it down some more. They slow down some more. They have less kinetic energy. Is there a lower limit to that, or can I just keep cooling it down forever? Can I just keep cooling colder and colder and colder, or would there have to be a lower limit?
There should be a limit when they don't move at all.
Yeah, when the particles stop moving, right, then you've reached the lowest possible kinetic energy, haven't you? And what kinetic energy would that be if they're not moving? Zero, right? Now look at that equation. If the kinetic energy is zero when the particles are no longer moving at all, what must the temperature be? The only way to get a zero for kinetic energy would be if T was equal to zero, right? So then the lowest possible temperature is the temperature where the average kinetic energy is zero. In fact, every particle would be stopped moving at that point. And so the logic goes, if that's the lowest possible temperature, why don't we just call that temperature, what value? Zero, okay? And then if that's the lowest temperature and we're calling it zero, then wouldn't every other temperature be a positive temperature?
Yes.
Do you follow that logic? If this temperature, which is the coldest possible temperature because the particles have stopped moving, if that one's being called zero on our temperature scale, then every other temperature above that is positive, isn't it? So with this new temperature scale, there are no negative numbers. They're all positive numbers. Does that make sense to you? And that's why we're going to use this temperature scale. It's called the Kelvin temperature scale. It's sometimes referred to as the absolute temperature scale. You might want to note that on the side there. It can also be called the absolute temperature scale. Just like in a math class, what happens? What does absolute value do? It makes negative numbers positive, doesn't it? So absolute temperature scale makes you have no negative temperatures. They're all going to be positive temperatures. The reason it's called Kelvin is because it's named after a physicist named Lord Kelvin, and that's Kelvin High School is also named after that person. Now there's a simple formula. If you want to convert between Kelvin temperatures and Celsius temperatures, you just take the Celsius temperature and add 273.15. Okay, write that down if you don't have this with you, or highlight it if you do. So Celsius temperature plus 273.15 gives you the Kelvin temperature. So what was the lowest possible temperature on the Kelvin scale? It was zero. So we give it a special name. We call it absolute zero. Have you heard of that before? Absolute zero, the lowest possible temperature. What would that temperature be on the Celsius scale? Right? If you let the Kelvin be zero, then the Celsius would be minus 273.15, isn't it? So minus 273.15 degrees Celsius is the same as absolute zero on the Kelvin scale. That's the lowest possible temperature, right? And why is there a lowest temperature again? Because the particles will stop moving. And when they stop moving, they have no kinetic energy. And if they have no kinetic energy, the temperature must be 0. Does that make sense? All right. So we're going to be using the Kelvin temperatures, not the Celsius temperatures. Yes, Samantha. Say it again. I can't hear what you're saying. You have to yell it out louder, or? I think I'm hearing what you're saying. So what I had asked was, if 0 is the lowest Kelvin temperature, I asked you, what would the Celsius temperature be at that, on that scale? So if the Kelvin temperature is 0, then the Celsius must be negative 273.15, right? Celsius temperatures can be negative or positive or 0. The Kelvin temperature scale can be 0 or positive, but there's no negatives because it's the lowest temperature. All right. Now, 0 Kelvin, the absolute 0, it's a theoretical temperature. Okay. We can never actually get there. We've cooled things down super cold in the lab, but never to absolute 0. We've gotten very close, like billionths of a degree, but we can't get there. And there's a simple reason. To measure the temperature of something, you have to somehow connect the thing you're cooling to something to measure the temperature with. And as soon as you measure the temperature with something, some energy gets in. And so the temperature goes up a little tiny bit. So we've been able to measure down to like a billionth or more or closer, but we can't quite get to absolute 0. Okay.
If we don't measure, will it be absolute?
So, but we wouldn't know. We wouldn't know. Maybe we are, but we just don't know. Okay, there's not here. Let me just give you one last little thing about absolute 0. If absolute 0 means there's no kinetic energy, and that means everything must stop moving. That's what that means. Does that mean inside the atom, the electrons stop moving? Electrons are flying around the nucleus. Do electrons stop moving? The answer to that is not simple to understand. It's no, the electrons don't stop moving, even though the kinetic energy is 0. And the reason for that we'll get to in grade 12 chemistry. All right. So we're gonna watch a video. It says 6 data points. We're not going to do 6. We're going to do 4. I was going to do a fake animation for this. Okay, a fake animation. If you're ever watching an animation on a computer, somebody programmed that, right? And when they programmed that, they used Charles's law to program it. So then when we watch the animation, we're getting correct results because it's based on Charles's law that the programmer used. So if I were to show you an animation, it would look cool and simple, but it'll be fake. All the numbers would work out perfectly because we're circular logic. So instead, I'm going to show you a little YouTube video. This YouTube video, the person does a sort of clever experiment, but it's got some errors involved. Charles's law is hard to study in the lab, at least in a high school lab. At home, you can see this. Yes, no?
Yeah.
Thank you. So this is Flynn's Science. It's a science company, and this is quick. We're not going to watch the whole 16-minute video. We're just going to watch part of it. But
In the ideal gas law,
hey, look.
and that the properties are independent of the nature
Okay,
of the
so
gas.
she's wearing safety goggles while using ice water and a syringe full of air. Okay, but that's good safety precautions. Wear safety goggles. So she's got some beakers here of hot water to cold water. The cold salt water is actually less than 0 degrees Celsius. It's around, you'll see in a minute, around -10 or something. She's got digital thermometers in them. So she's going to tell us the temperatures, and you're going to record the temperatures in your data table. She's going to tell us the temperatures in Celsius. Your data table says Kelvin. So what you might want to do is write the Celsius temperatures above the data table, and then in a minute we'll convert them to Kelvin on our calculators, and then we'll put them in the data table. And then she's got a syringe. I'm going to skip ahead here. I know none of you guys do this when you watch my videos, right? You don't just skip ahead. You watch every moment in my video because it's very informative and interesting. So she's got a syringe, and she's going to cap the syringe. Why is she going to cap it? So that nothing can get in or out. We want the amount of gas to be held constant, right? The syringe has a plunger, though, that can move up or down. Now here's one source of error. That plunger, there's some friction between the plunger and the plastic wall. So it's not perfectly, smooth. That's going to provide some resistance as it tries to move. And that's a source of error. She's lubricated it to make it move easier, but still that's a source of error. Okay. She's going to take some air in the syringe, as you can see here. She's got air in the syringe and she's plunging the syringe into the cold water bath here. And then she's going to let it sit in the cold water bath for a while. And once it's cold, she's going to read the volume of gas. Does that make sense? But to read the volume, she has to take it out of the cold water to read the volume. And what does that mean? As she takes it out of the cold water, it's going to start warming up again. And so the volume will change. So she's got to work quickly. But even if she doesn't work, if she works quickly, that's a source of error. There's several sources of error here. Okay. Let's see what she does.
At that temperature. And normally if I were doing this in a classroom with students, I would say to keep it in there for about 2 minutes. And what I'm going to do is, it stays in there pretty easily. We'll talk just a little bit.
Is the air in the syringe fully submerged in the ice water?
And a couple of
If it's not, that's another source of error, right? All right, let's go ahead. Come on. Come on.
You a quote.
Okay, come on.
That's what we're going to
We don't want your quote. Here we go.
See where it rests.
All right, so get your data table ready. So she's just recorded the temperature. It's -9 degrees Celsius. Okay. The 15.1, don't write that down. That's the volume in the air. So that's the volume before she put it in anything. It doesn't, I don't know why they recorded that. We don't need that. So -9 is the first temperature. Write that down above where it says temperature on your handout. -9 degrees Celsius. And now watch what she does. She pulls it out of the ice water.
Overcome a little bit of resistance.
It's warming up.
Warming it up
Okay.
too much. I'm going to immediately measure the volume of that, and I'm reading 13.0.
Okay, so she puts it on the table, she looks at it, it goes around 13.0. Okay, put that down as your volume, 13.0 milliliters. Okay.
13.0. Okay, I'm going to push that in. And we're going to go here with a temperature of 0.5.
So now she has it in normal ice water, 0.5 degrees Celsius.
Just a little while longer to equilibrate. I only need the sample of gas, obviously, in the bath, whatever the temperature of that bath is. What I'm going to do here,
2 minutes later,
we said that was at 0.5 degrees, right? And we're going to go ahead and do the same thing. We're going to press that in.
What she does is she pushes the plunger in slightly, which sort of overcomes the friction, and then it gets pushed out again. And when it stops being pushed out, she reads the volume. Does that sort of make sense? So push it in slightly just to get it moving, let go, and let it come back out again and stop. And then she reads the volume. Okay.
I'm just pressing it in until the lip.
All right, so we're going to skip ahead here. 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 Skip ahead here.
Going to take that out. I pressed it.
We want to see the data table. Show us the data table. There we are.
13.
All right, so that's what we want to write down. So 0.5 degrees. The volume was, hey, look at that, 14.0. Do you raise an eyebrow when you see that? 13.0 and now 14.0. I'm a little suspicious we're not reading these volumes very accurately. And look, the next one's 23.8 degrees Celsius. So that's room temperature. And look, 15.0 again. What? These are all 0.0. This person's not reading these volumes super accurately. And then 70.8 degrees Celsius and 17.0 mils. You might as well not put the point zeros, right? Because you're not reading them accurately. So it's 13, 14, 15, 17. All right, everybody's got those written down? Grab your calculator. Let's quickly enter the data on our calculators, okay? So zoom in here. Okay, if you have your graphing calculator, turn it on. Let's go. Dimitri, do you have yours there?
I'm waiting. Did until it gets delivered.
What's that beside you?
It's the usual calculator.
Oh, okay. I've got another one here. I think that works.
Thank you.
Doofus, I was going to give you that one the other day when you told me that, and then you left and you went down the hallway. In any case, I've just given out the two I have, the extra ones. I don't have any others than that here. So for now, you just have to watch. Okay. All right. So we are going to quickly analyze this data graphically. Okay. So press your stat button on the calculator, stat. And do you remember, if you've used it before, go to number 1, edit. That takes you to your lists, right? Do you remember how to clear the numbers that are in there? Put your cursor up on top of the L1 symbol, press clear and enter. That'll delete all those numbers. Do that again for all of them. Put your cursor on top of the L2, press clear, enter, and do it again if there's stuff there. Clear, enter. Okay, now quickly enter your data. Let's put our Celsius temperatures in the first column. -9. Be sure you're using the negative symbol, not the minus button. The negative symbol's at the bottom of the calculator, right? Not the minus button on the right-hand side. So -9, enter. 0.5, enter. Keep going, 23.8, 70.8. Then go to the next column and let's enter the volumes. 13, 14, 15, and 17. Okay, now we can graph this and we would get a good graph, but those temperatures are Celsius temperatures, right? Let's convert them to Kelvin. So go to your third list and put your cursor. Now there's two ways to do this. One way would be, don't do this yourself, but one way would be right here. I could say -9, which was the first temperature, right? Plus 273.15 equals. And now I can go 0.5. I could do this one by one. But do you get a feeling I paid $200 for this calculator? There better be a better way to do that. There is. Put your cursor on top of the L3 symbol. And do you notice at the bottom, it now says L3 is equal to, right? So it's waiting for us to type something. We want to convert the temperatures to Kelvin. Where are the temperatures right now? They're in list 1. So let's, right above your keypad, 1, 2, 3, 4, 5, 6, it says L1, L2, L3, right? So let's go second function L1. So we're going to say list 3 is equal to list 1. And what do we do to all those temperatures? We add 273.15. Does that make sense? Take all the numbers in list 1 and add 273.15. Press enter. And now they all get done at once. Make sense? So now remember where the numbers are. List 3 is our Kelvin temperature. List 2 is our volume, right? So let's make a graph. Where do I go? Where do I go? I go right above the y equals to stat plot, right? So go second function, stat plot. I've used this before. So for me, plot 2 is right now turned on and plot 1 and 3 are turned off. It doesn't matter which one you use. You can use any of the plots. So you could use the one that's turned on. If none of them are turned on, then just use any of them. I'll use plot 2 because it's already turned on. If you didn't have one of them turned on, then you've chosen plot 1 or plot 2, then now you have to turn it on. So put your cursor on the word on and press enter, right? Mine was already on. The type is the first type. That's our scatter plot. That's what we want to see. The X list, where are my X values? Well, it depends. What do we want to graph? We want to put volumes on the Y axis, and we'll put temperatures on the X axis. So which list has our Kelvin temperatures? List 3. So you want list 3 to be the X list. Now, what do we want on the Y axis? We want volumes. And where are our volumes? They're in list L2. So we want L2 to be the Y list. Is this making sense? The mark doesn't matter. It's just what do you want the points to look like? It doesn't matter. And the color doesn't really matter, right? You can change the colors if you like. Now I want to see the graph. Do you remember the fast way to see the graph? You press? No, not graph. The problem with pressing graph is that whatever the last window settings were, like the X minimum and maximum X, minimum, maximum Y, it'll graph this graph on those window settings. And those might not be the right window settings. So you might not see your graph. So what do you want to do is press zoom. And which one of these options do I want? We were making a stat plot, weren't we? We were making stat plot. So which one do I want? Number 9, zoom stat. And there's my graph. Okay. On your paper, if you're doing this at home without the handout, sketch this graph. For those of you that are here in class, you can, or if you have the handout you're at home, we'll do a quick rough sketch on this grid. Okay. So if you're doing this at home without the handout, then just sketch a graph on your loose leaf. For those of us who have the handout, we're going to move fast. We're not going to plot this accurately. We're just going to sketch it. So we have temperature in Kelvin. We have volume in milliliters. Notice the graph on my calculator doesn't really show me the window settings, does it? So if you press window on your calculator, press the window button, you can see the minimum and the maximum for everything, right? So my minimum is 256, my maximum is 350. So why don't I say this is around 250 minimum, and this is around 350 maximum, right? Approximately. And the volumes, the minimum on my calculator says 12.32. So I'll just say that's around 12. And my maximum is around 18 milliliters. And now what did the graph look like? Well, there's a point here, there's a point here, there's a point here, there's a point here. Okay, something like that. Now, if you have a choice of only 2 options, it's either an inverse, a hyperbola relationship, or it's a direct straight line relationship. Which of those 2 choices does this most look like? Hyperbola or straight line? It's not a perfect straight line, but a straight line is much better description than a hyperbola, isn't it? So then we would say that this is a directly proportional relationship. Okay, we can say it's directly proportional, and our graph basically looks like this, doesn't it? Let's prove it. If you have your calculator there, let's prove it. Okay, so come on. Why does it? Sometimes this calculator works beautifully under the document camera, and sometimes it's horrible. And I don't know why. Whoops. All right, so we're going to go to the stat menu again. Stat. And this time we're going to go to the right-hand side. Oh, come on. Why is it doing this? We're going to go to the right-hand side to the calculate menu. So stat, and then calc on the right. And I think we did this yesterday, didn't we? We're going to try to find an equation that goes through our graph and says, because our graph looks like a straight line, which one of these are we going to use? Lin reg, which means linear regression, which means find the equation of the line, right? So let's choose number 4. Most of us will have this menu right now. Some of us, it'll just say at the top, lin reg.
Yeah.
If yours just says lin reg, hold on for a moment. For those who have this menu, where are our X values? They're in list 3. So make the X list, list 3. Where's your Y values? They were in list 2. So make the Y list, list 2. Then go down to the store regression equation. We're going to tell the calculator to store the equation that it generates and graph it. So now that you're at store regression equation, press the vars button, which means variables, vars. It's right underneath the arrows on your calculator. And go over to Y variables, the Y vars, and choose functions. And choose any of these. I'll choose number 1. So we're saying perform linear regression on the data in list 3 and list 2, my X's and my Y's. And that means find the equation of the line. Then we're saying take your equation and graph it for me as function Y1. Press enter and enter. There's the equation of the line, right? For those of you who don't have that menu, your screen right now just says lin reg at the top.
Yeah.
So type in where your X list is right now. It's in list 3. So do a second function L3. Now it says lin reg L3. Put a comma. The comma is right above the number 7 on the keypad. There's a button for comma. And tell it where the Y values are. They were in list 2. And then put another comma because you want it to also graph for you. And press that vars button, variables, go over to Y variables, choose functions, and say Y1. And now your calculator should say lin reg L3, comma L2, comma Y1. Press enter. And it should show you the equation of your line, right? Now press graph. And there's the line being graphed for us, right? On your handout, sketch a line like that, okay? This data, as we mentioned in the video, has lots of sources of error, so it's not a perfect straight line, okay? But it's pretty good, okay? What's the equation of a straight line that goes to the origin? It's y equals mx, right? Just mx if it goes to the origin. But we don't have x and y. We have volume and temperature, right? So instead of y equals, this is going to be what? V equals. And instead of m for slope, what symbol were we using in our notes?
K.
We were using a K. And instead of x, what's on our x-axis? No, that's the unit. What's on the x-axis? It's temperature, right? So capital T. V equals KT would be the equation of our line, right? If you press on your calculator the y equals button, you'll see the equation has been plotted for you as function y1, but it has all these stupid decimals, doesn't it? As a chemistry teacher, I'm hugely offended by all those sig figs. So let's round it off. Mine says 0.0474. I'll keep two digits. So 0.047. And then you see the DEL button? That means delete. So just delete all these other digits, but don't delete the X. You need the X, right? So 0.047X plus, I don't need all these other digits too, 0.769 or maybe just 0.77, and then delete all those other numbers. So now I have a much simpler looking equation. According to our experiment, the actual equation is V equals 0.047 T plus 0.769. That's the actual equation of our graph. It's not supposed to have a y-intercept. It's supposed to be 0. It has a y-intercept because there were errors in the experiment, right? The syringe not being at the exact temperature, all those things. Okay. One interesting thing we can do before we leave this, go back to your graph Okay, go back to the graph. And let's change the window settings. Okay, go to window. Its minimum temperature right now is 256 Kelvin. What is absolute zero? It's 0 Kelvin, right? It's supposed to be the lowest possible temperature, isn't it? So why don't we set the minimum temperature to be 0 and the maximum temperature to be 400. Okay, so that will include all of our data, won't it? And then the Y values, these are volumes, aren't they? The minimum volume would be 0, right? That's the smallest volume you could have. And the maximum volume, it was 17.68. Why don't I just say 18? Okay, now your Y scale, I don't think this really matters, but if you're going from 0 to 18, what would you go up by on a graph? 2s or 4s or something? Let's go up by 2s. It doesn't really matter, the scale. And now press graph. Do you understand what we just did? We changed the window. So now it starts at 0 on the x-axis and goes up to 400, I think we said, or 300, whatever it was. So all of our data is way up here, right? And then what is this way back here? This is the line we just calculated. And where's it headed? It's headed towards absolute 0, isn't it? But because of errors, it's not exactly hitting absolute 0. It's got that little y-intercept, doesn't it? Can we calculate what it thinks the lowest temperature is? We can. It should be 0, but it looks like it's going to be at negative something, isn't it? So let's go change our window setting again. Instead of 0, let's go negative 40. There is no negative temperatures on the Kelvin scale. I know, but our data is sort of showing us a negative one. So now press graph. All right. So according to our data, it's crossing the x-axis at around what? Negative 30 or so? Sorry, negative 20 or so. Do you get that? And we could actually calculate it. We can go second function calc. We could calculate exactly where it thinks that the x-intercept is, but we won't, okay? My point, though, is that you could use the experiment we just did, right? Imagine you didn't know absolute 0. Imagine you didn't know it even existed, right? You could take your data here and extrapolate it like we're doing here, and you would discover there must be a lowest temperature. Why must there be a lowest temperature? Because your volume gets smaller and smaller and smaller. What's the smallest volume? 0. If there's a smallest volume, then there must be a smallest temperature as well. Does that make sense logically? So you could use this simple experiment that this lady did to estimate the value of absolute 0. It's kind of cool, okay? All right, on your handout, going back to it, flip to the 3rd page, or for those of you who don't have the handout, you can simply jot this down on your loose leaf if you want. We have these temperatures. If you press your stat button on the calculator and choose edit again, stat and edit, you can see the temperatures and the volumes. The Kelvin temperature was 264, then it was 274, then it was 297, then it was 344. Those were the Kelvin temperatures. I'm just looking at my calculator. The volumes were 13, 14, 15, and 17. We just finished saying that V was equal to KT, the equation of our line. If V is equal to KT, then K is V divided by T, isn't it? So V divided by T should be constant. Let's see if it is. Look at your data. There's my V, there's my T. Let's divide them. So on your calculator, if you go second function quit, right above the word mode, second function quit, it takes you back to the main screen here. Okay, so let's do 13 divided by 264, V divided by T. This gives me 0.049. Do it again, 14 divided by 274. Yeah.
Can we also do that in the math part of the calculator?
Yes, you could. Yeah. We're doing it here just because it's on the handout. 15 divided by 297, 0.051. And 17 divided by 344, 0.049. Okay. Given that there was error in our experiment, are you satisfied that that's essentially constant? You know, around 0.05, right? And finally, if K is equal to V divided by T, if that's true, then a V1 over a T1 should equal a V2 over a T2 because they're both constant, aren't they? So coming back here, rewrite the equation, show how we get this. V1 over T1 equals V2 over T2. Let's just quickly do what I just finished saying. V over T is constant. Therefore, a V1 over a T1 is constant. And a V2 over a T2 is also constant. And put those together, V1 over T1 must equal V2 over T2. All right. That is the normal version of Charles's law. Okay. When you're using this law, temperatures must be in Kelvin. Okay. Temperatures must be in Kelvin. No choice. Volumes can be any unit as long as they're the same. Okay. But temperatures have to be Kelvin. Okay. All right. I got about 10 minutes. I'm going to squeeze in some other stuff. I was going to do another lab video with you on YouTube, but I don't think we have time. So we're going to switch back to the PowerPoint notes. So everybody's on the same page at this point. Okay, so I'm going to quickly go through what we've already done. You decide if you want to write anything extra down. Okay. Say again.
We didn't take these notes down yet.
So the Boyle's law, and as you're about to see Charles's law, you have handouts on those. So you don't necessarily need to write this down. But if you look at this and go, well, I don't think I knew that, or I didn't have that on the handout, you did have it on the handout. But if you think you didn't, you could write it down now. I'm going to zip through this. So Boyle's law, here's what you need to know. He studied pressure and volume. He discovered that they were inversely related. And of course, that means that when the pressure goes up, the volume goes down. It also means if you made a graph of pressure versus volume, you'd see a hyperbola. And to make it linear, you'd graph P versus 1 over V, or V versus 1 over P. It doesn't really matter. So volume is proportional. This is a font error. It's supposed to be the proportional symbol, the little alpha symbol. Volume is proportional to 1 over P, or V equals K over P. That's just inverse relationship, which means P times V is constant. Now we're at Boyle's law. If P times V is constant, then a P1 V1 must equal a P2 V2. And this is only true if temperature and moles are held constant, right? P1 V1 equals P2 V2, inversely related. And you can use any pressure units as long as they're the same. You can use any volume units as long as they're the same. Okay? Then we looked at Charles's law. Charles studied, we just did this today, studied volume and temperature. The temperature, though, was the absolute temperature, it was the Kelvin temperature. He discovered a direct relationship not an inverse. So a graph of V versus T was not a hyperbola, it was a straight line. Because it was a straight line, V is equal to KT, just like Y equals MX. And that means V divided by T is constant. So a V1 over T1 would equal a V2 over T2. This is what we just finished doing, right? And this is only true if pressure and the amount of gas are held constant. In this equation, we have to use Kelvin temperatures, but any volume units would be acceptable as long as they're the same on both sides. All right. We talked about the absolute temperature scale and kinetic energy. Temperature is a measure of average kinetic energy. That's what it is. The higher the temperature, the faster particles are moving, right? And if they're moving faster, they have more energy, they collide with more force, all of that, right? Kelvin temperature is degrees Celsius plus 273.15. Do you notice a little quirk there? Celsius has a degree symbol. Kelvin doesn't, okay? Kelvin is not degrees Kelvin. It's just Kelvin, okay? All right, here's some new stuff. Everybody should be jotting this down. There were 4 variables. We can pull 2 of them out in lots of different ways. We've done Boyle, we've done Charles. Here's Avogadro's law. Now, let me back up a bit. Avogadro studied the effect of amount of gas on volume. Okay? Let's see how good your logic is. Ready? What does your gut tell you this relationship must be? Volume and moles. If you put more gas in the balloon, you increase the moles of gas. What happens to its volume? It gets bigger, doesn't it? If you blow more gas in the balloon gets bigger. Now, Avogadro knew that, obviously, but that doesn't necessarily mean it has to be a direct relationship, right? In the real world, it doesn't have to be a direct relationship. There's other ways that could happen. But we're cheating, and I'm already telling you, it's either a direct or an inverse relationship. So if you know it's got to be one of those 2, and you understand more gas makes the volume bigger, then what did he discover? Which relationship? It's going to be a direct relationship. And what does that mean about a graph of moles and volume? It's a straight line. And then N must equal KV, right? Or V must equal KN, it doesn't really matter. And that means an N1 over V1 will equal N2 over V2, just like Charles discovered, right? And sure enough, that's what Avogadro found. So volume and temperature are directly related. So a graph of V versus N is linear. V is equal to Kn, the straight line equation. So V divided by N is constant. And a V1 over N1 equals V2 over N2. Is it mathematically obvious to everybody that you could flip that over and it would still be true? You could say N1 over V1 will equal N2 over V2. Is that obvious? If 2 fractions are equal, won't their reciprocals also be equal? Can I get a yes or no? Is that obvious? So when I write Avogadro as V1 over M1 equals V2, if you saw in another source, no, it's N1 over V1 equals N2 over V2, you'll just go, that's the same thing, isn't it? Just another way of saying it, right? Then what did Gay-Lussac study? Well, his name was Joseph Gay-Lussac. I don't know how they knew he was gay. It's kind of interesting. But anyways, Gay-Lussac's law, okay, he studied pressure and temperature. Imagine taking a steel can, okay, it's steel, it's rigid. cannot expand, cannot contract. Its volume is constant, right? Fill it with gas. Now start heating it up. Would that be smart to do?
No.
Why not? What could happen if you start heating this can full of gas?
The volume will increase.
Okay, the volume can't increase because it's solid steel. It's rigid.
Then the pressure will.
Oh, so Dimitri's saying the pressure will increase, and I see Madeline saying it could explode. Right? Do you guys remember in grade 9? Did anybody ever accidentally heat a flask or test tube that had a stopper in it? You ever do that by accident? What'll happen? The stopper will pop off. Why does it pop off? Because the pressure inside is increasing. Why is the pressure increasing? Because when you raise the temperature, you're raising the average kinetic energy of the particles. So they move faster. And that means they collide with the container with more force. And if they collide with more force, that creates greater pressure, doesn't it? So what kind of relationship does he discover? When the temperature goes up, the pressure goes up. This is a direct relationship also, which means a graph of P versus T would be linear. P will equal KT. A P1 over a T1 will equal a P2 over a T2. Do you see how it's all the same as soon as you realize it's directly proportional? It has to look exactly like Avogadro, has to look exactly like Charles. Okay. All right. I'm going to just give you a glimpse. I don't want you to write it down. I'm just going to give you a glimpse of where we're headed here. All of these laws we've looked at, and there are more, they all just have 2 variables in them, right? We just studied 2 at a time. You can put them all together. You can put all 4 variables together and call it like the master gas law, the gas law to rule them all. Okay. Look at that. Don't write it down. I'll give you 10s on Monday. Just look at that for a moment. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Suppose you were to hold the moles and temperature constant. Suppose you held them constant. Then wouldn't the moles and temperature just cancel if they're the same on both sides? And what would you be left with if the moles and temperature cancel because they're constant? You'd be left with P1 V1 equals P2 V2. Hey, Boyle's law. What happens if you hold pressure and moles constant? Pressure and moles. They would cancel out on both sides. Then what would you be left with? V1 over T1 equals V2 over T2. All of the gas laws can come right out of there if you hold 2 of them constant and just cancel them out. All right. All right, folks, enjoy your weekend. Okay. We got next week, things are going to explode in difficulty. Okay. Because we're going to start using all these gas laws in problem solving. Okay. With that bright note, have a lovely week. Okay.